Okay, hi guys. Thanks for coming to the math club meeting.
Hi Tristan.
Hi Jason.
Hi, Tristan.
Today I want to talk about numeric solutions, which is a way to solve several equations. And this is probably not going to come up on the UIL math test, but I think it's really interesting and I think that you're going to enjoy it as well. Okay, so if we go to the next slide. One of the problems we're going to solve today is solve x equals cosine x. Let's assume x is measured in radians. It doesn't really matter, but let's just assume it's in radians so we get the same answer. And I want you guys to try and solve it for like 1 or 2 minutes before I tell you the solution. You can use your calculator, but you're not allowed to use the equation solver and you're not allowed to do graphing. So try it.
Oh my gosh, I'm actually so good. Wait, Jasmine, you do the last question. That seems like a good test.
Okay, did anyone solve it?
Oh yeah, that was so freaking easy.
Okay, how can we possibly solve this equation? So unlike most equations from school, x equals cosine x cannot be solved analytically. That means it's impossible to write down the exact value for the solution in terms of familiar. Can you go to the next slide, please?
Yeah.
In terms of familiar functions like logs, powers, and roots. But we can find an incredibly accurate numerical estimate using a very simple trick. So I want everyone to try this. Set your calculator to radians first, then type in any number. You can type in 0.5, you can type in 42, any number you want. Then type cosine of answer and then spam enter. Just type cosine of answer over and over. And let me know what number you end up getting. Just press enter, type cosine of answer and then press enter again and again. So what did someone tell me what you got?
0.450183611.
Is it in radians?
Yes.
Okay. 0.451.
0.1836.
Yeah, I got 0.739.
What?
Yeah, that's not what I got.
0.73.
0.735. I got 0.9. Within degrees. 0.74.
Yeah, I got 0.73. I got 0.739.
Okay, so you can start with any number, right? I'm sure that not everyone in this room started with the same number, but you guys all should have ended up getting the same number. It's like 0.735. So the answer to the first question, does the final number depend on what you entered initially, is no. You can enter any number initially and you get the same final value. And the answer does satisfy x equals cosine of x, right? Because if you take cosine of this number, you get the same number again. So we found a solution to x equals cosine x without using the equation solver, without graphing, by just spamming cosine answer on the calculator. Can we use this to solve other equations? This technique is called fixed point iteration, because a fixed point of a function f is a value x such that f of x equals x. And we found a fixed point of the function cosine of x. Let's try to understand why this works. I will draw the graph of cosine x. This is y equals cosine x, and this is the line y equals x. So let's say that x naught is your initial guess. Let's say your initial guess was like right here. So this point is x naught and y equals 0. You can visualize it like a spiral. So the rule is that you first go up to the function, and then you go horizontally to the line y equals x. And then you go to the function, go vertically to the function again, and then you go to the line y equals x. And you repeat this. And in this case, you end up going to that point, which is the solution. It's the intersection point of the line y equals x and y equals cosine of x. Why does this work? This point, so why is this spiral that I drew the same as what we did on the calculator? Because this point has a x coordinate x naught, and its y coordinate is cosine of x naught. And then this point, its x coordinate is cosine of x naught, and its y coordinate is cosine of x naught. And this point, the next point on the curve, its x coordinate is cosine of x naught. So as you can see, the x coordinates of the points on the curve is just taking cosine more and more and more times. So that's why what you did on the calculator, spamming cosine of the answer over and over again, is the same as this spiral. And because this spiral ended up terminating at the solution, your calculator also ended up converging to the solution. Okay. So anyone want to try to find the solution to x equals tangent of x over 2? What do you get if you try the same thing?
0.
Okay, find a non-zero solution. The 0 one is too easy. We have to make it harder. So this is the graph of y equals tan of x over 2, of y equals tan of x over 2. And also graph the line y equals x. And I want you to find a non-zero solution. So I want you to find this root. This one is too easy. I want you to find one of these. Yeah.
Is the solution x equals 0?
That is one solution, that's correct. But we need a non-zero solution. There's 3 solutions in this image. You can find one of these.
Wait, Mr. Sun?
Yeah. You don't have to call me Mr. Tristan is what?
I keep spamming cosine for like the one before this.
Yeah.
And I keep getting different numbers.
You did cosine of the previous answer? In your calculator screen, did you catch?
Where did you do that? So you just round to the
How much is
thousands, I guess.
Spend enough time to just get something.
Wait, did anyone figure out how to do this one?
Wait, just give me like 30 more.
Okay, Jason. Okay, so if you try this, as I think some of you realize, if you just do spam tan of answer over 2, you're going to find the root x equals 0. And we can figure out why that is. But the way to do this is that you take inverse tangent of both sides. So we can rewrite it as inverse tangent of x equals x over 2. So then you can say that 2 times tan inverse of x equals x. If you go to the next slide, please. I put the graph of inverse tangent on the next slide.
Oh, this one?
Wait,
Okay, there you
Mr. Sun. Is the answer 2.3?
It is.
Oh, no way.
Good job, Jason.
Okay, so if you rearrange the function, now it'll converge to one of those roots. And if you want to see why, let's draw the graph again, and we'll repeat the process of the spiral. So let's say that this is the spiral. And let's say that my initial guess is x naught. First I'll go vertically to the line, to the function, and then I'll go horizontally to the line. and then I'll go back to the function again. And as you can see, if you start with a guess x naught, which is greater than the solution, then you'll end up converging to the solution, going to the left. And if I guessed over here, then it would be the same, but you would go to this root. So you can find the positive root and you can find the negative root. And if your initial guess was like less than the root, then you go to the function and you still end up finding the root. So no matter what value you start with, you'll find one of the roots. So is that how you did it, Jason?
Absolutely. No, I had the number on my calculator. I didn't just read it off.
What is
Arc is the same. Arc tan is the same as tan inverse. Like, so like if you say tan of x equals y, then arc tan of y equals x. Okay. What another similar equation? Try to solve x equals e to the x minus 1 over 2.
Are we supposed to like?
Find a non-zero solution.
Are we meant to crank it or like analyze it?
Do whatever you have to do to get the solution.
We've not been Henry, you gotta crank it.
I only have one hand.
Are you videoing the whole thing?
He asked me to.
I was just gonna tell.
I'm sorry, Mr. Sun, but I have other commitments. I must go to. Yeah, I got it.
What do you get?
1 equals 2, 5, 6, 4, 3.
Yeah, that seems right. Good job. How do you do it?
Same thing with the arctan.
Okay.
Nice. But we got multiplied by 2.
Okay.
Added 1, took the natural log. So we got natural log of 2x plus 1 equals x.
Okay. Yeah. So Ethan just rearranged the equation, right? You put the 2x on the left hand side and equals to e to the x minus 1. You can move the plus 1 to the other side, and you take ln of both sides. So ln of 1 plus 2x equals x. And then if you spam this one, the graph actually looks different, and you can find the non-zero root with this value, with this graph.
Is this,
Just one slide.
oh,
Multiplied 5. And then I plug that in. And
oh, there it is.
So we can understand why this one worked and why this one didn't by visualizing the spiral process. So this is the graph of ln of 2x plus 1 and the line of y equals x. If you start with x naught over here and you do the spiral, you'll converge to this root. And if you start over here, you'll also converge to that root. If you started with a negative initial guess though, like if I took x naught over here, then you would have gone down, but then you would have diverged. So it does matter what value you start with. You can't just choose any value in this case. So if your x naught is positive, you would end up converging to the solution. If it's over here, you would not end up converging. And we can also understand why iterating this directly doesn't work. Because if you imagine doing the spiral again, it will always go to the zero root. It won't find this one, which is what we're interested in.
Or if you pick something past 1.2 something, it'll
Yeah, if
diverge.
you go pick something over here, then it'll go
Yeah.
start diverging that way. Okay, so now we're going to give a formal proof that if the derivative is less than 1 for all x, then fixed point iteration must converge to a solution. For example, this condition is satisfied for y equals cosine x, right? Because for cosine x, the derivative of cosine is sine. And the value of sine is always less than 1 for all values.
And greater than 0.
Can you play the mean value theorem video?
No way, MVT in my face.
Yeah, we're gonna use mean value theorem outside of your calculus class. Oh. Okay, never mind. I'll just explain. Let's take any function. This part of the presentation is like optional. If you want to know a proof of more rigorous proof about why it works, or the specific case of y equals cosine of x. So mean value theorem says that if you have a function defined on the real numbers, on the value from a to b, there is a point where the slope is equal to the average slope. So here the average slope is from here to here. This is the average slope. This line is the average slope. And there must exist a point on the curve such that the slope of that point is equal to the average slope. If we can write this in symbol, for any function f, there exists some c there exists a c on the interval a, b such that this is true. Okay, you go to the next slide, please. Let's let x star be the unique solution to x equals cosine x. So x star equals cosine x by definition. And let's let xn be the nth value of your calculator. Okay, so x naught is your initial guess, x1 is cosine x naught, x2 is cosine x1, and so on. So what is x infinity? Like, right, if x1 is cosine of x naught and x2 is cosine of x1, like what happens if you just consider when the subscript goes to some really large number? Like x2 is equal to cosine of x naught. x3 is equal to the same thing, but you write 3 cosines. So what is x infinity?
Cosine of 3 minus 1.
0.739.
Yeah, exactly. X infinity is equal to x star, right? It's just equal to the solution. Because it's just what happens when you take cosine of x naught an infinite number of times. So x infinity is equal to, you just keep taking cosines of x naught. There's like an infinite number of cosines. Yeah, so x infinity equals x star. And what is xn plus 1 in terms of xn? Yeah. Okay, next slide, please.
Oh, okay, sorry.
You're good. Okay, let's define something else. Let's define the error. So En is defined as xn minus x star. And we want to show that this error gets smaller as you keep spamming. Each time you press the button on your calculator, we're going to prove that the error gets smaller. Okay, so let's say that En is defined as xn minus x star. So obviously you can say that En plus 1 equals xn plus 1 minus x star, but we can rewrite this, right? So what's an equivalent expression for En plus 1? Yeah, cosine of x. We know that xn plus 1 equals cosine of xn. So let's substitute this into here. Okay. And now from the mean value, let's apply the mean value theorem now. So we know that cosine of xn. Oh, also we know that x star equals cosine of x star. Do you agree that this equals En plus 1? This is En plus 1?
Wait, can I see?
Yeah.
Yeah, I agree.
Okay. By the mean value theorem, we know that there exists some value c such that this is equal to negative sine of c, right? Because the derivative of cosine is negative sine. Okay. So this is equal to En plus 1 on top, and the bottom value is equal to En. And it's equal to negative sign of C for some value of C. Because this was equal to En plus 1, and this is equal to En. So now we know that the ratio between the two errors is equal to some value sine C. But the value of sine is always between negative 1 and 1, right? The absolute value of sine x is always less than 1, less than or equal to 1. So that means that the ratio is always getting smaller. En plus 1 is equal to En times sine of something. It's really not important what's in the sign. But because sine is always has a magnitude less than 1, that means the magnitude of En plus 1 is always smaller than the magnitude of En. So the error is always decreasing, and that's why it converges. That's all. Thank you for your attention.
Mr. Stein.